IR spectroscopy. It is also called as vibrational spectroscopy. Here, all the molecules present in the sample solution will be vibrated by electromagnetic radiation. All molecular vibrations are useful for analyzing the sample, but how? How it happens? How exactly all these molecular vibrations are useful for identification of the sample components as well as identification of the functional groups present in the sample solution. Please watch this video till the end. If you have any doubts, please ask in the comment section below and don't forget to subscribe my channel. Okay, let's get into the main topic. First of all, we should know how molecular vibrations are generated in atomic level. Let me explain with an example. Here I'm taking water molecule as an example. This is the atomic structure of water molecule. Here I'm passing UV visible radiation through which here I'm passing about 10 to 700 nanometer wavelength range. At this wavelength range, here we can see the electronic transitions. Electrons which are present in the valency shell will be excited to the higher energy levels. But these electronic transitions will not be providing any molecular vibrations. Let's go with IR radiation. So we are passing around 700 nanometer to 1000 micrometer, so which is IR radiation wavelength range. And here we can see the molecular vibrations. But what is the reason why IR radiation is only producing molecular vibrations but not UV visible radiation? So this picture will be explaining the reason. Here IR radiation, so which is having higher wavelength when it is comparing with UV visible radiation. But there is a relationship that E is inversely proportional to lambda. Here wavelength. So when we are having higher wavelength, so which is producing less energy. In this case, IR radiation, which is having higher wavelength, so that's why it is producing less energy to get the molecular vibrations. But all IR frequencies are not useful for creating molecular vibrations. Let me explain with an example. Here I'm taking water molecule again. I'm sending near IR region, that is 700 nanometer to 1400 nanometer wavelength range, but I could not get any molecular vibrations. Let's go with far IR region, that is 4000 nanometer to 1000 micrometer. Here also we cannot get any molecular vibrations. And finally, I'm trying with mid IR region, that is 1400 nanometer to 4000 nanometer. Here I could see the molecular vibration. What is the reason? So why specifically at this region, here we can get the molecular vibrations. Here every molecule or atom will be vibrating with its natural frequency. It is a characteristic frequency. So when this natural frequency is equal to applied frequency, then we can see the molecular vibrations. So different bonds, different functional groups are having different natural frequencies. So by identifying these natural frequencies, we can identify the bond types which are present in the molecules. Do you think all the molecules are vibrating in the same manner? No, it's not. There are two types of vibrations will be there. So first one is stretching vibrations and the second one is bending vibrations. In stretching vibrations, bond length is altered. In bending vibrations, bond angle is altered. Stretching vibrations will be two types, symmetrical stretching and asymmetrical stretching. In symmetrical stretching, two bond lengths are increased or decreased in length symmetrically. Whereas in case of asymmetrical stretching, here one bond length is increased and the other one is decreased. Coming to the bending vibration, here we can see the change in bond angle. So these bending vibrations will be four types, in which two vibrations are in plane vibrations, rocking and scissoring, and two vibrations are out plane vibrations, wagging and twisting. In rocking, here the bond angle is maintained, but both bonds move within the plane. Whereas in case of scissoring, here bond angle is decreases, but it is moving within the plane. Coming to the wagging, here wagging, the both atoms move to one side of the plane. Whereas in case of twisting, here one atom is above the plane and the other atom is below the plane. All the atoms are not providing these all type of vibrations. So it is depending upon its natural frequency. All molecular vibrations are not IR active. Let me explain with an example. Here I am taking carbon dioxide, which is providing four fundamental vibrations. Why? Because carbon dioxide is a linear molecule. So this is the formula 3n minus 5. So when we are substituting n value here, we can get the 4 fundamental vibration. So here n is number of atoms present in the molecule. The first stretching that we can see here is stretching vibrations for carbon dioxide, but these stretching vibrations are IR inactive. Why? Because here we cannot see any dipole moment change. So that's why these type of stretching vibration that we cannot see on the spectrum. And the second type of stretching vibrations are called asymmetric stretching. Here we can see these stretchings on the spectrum at 2350 centimeter inverse wave number. And the third type of stretching is called bending vibration. Here we can get the two bending vibrations. So at 666 centimeter inverse wave number, but these two vibrations are moving at the same frequency. That's why we can get a single vibration on the spectrum. So this is the spectrum of carbon dioxide. So here we can see two bands. The first band at 2350, this is asymmetric stretching, and the second band at 666 centimeter, so which is bending stretching, bending vibrations. Okay, so that means here we can get the two bands only. Actually, the carbon dioxide is providing four fundamental vibrations. So that means the number of fundamental vibrations which are not equal to number of IR active vibrations. Let's go with Hooke's law. So what Hooke's law is telling about is it is telling about the bond position of that particular functional groups. So this is the Hooke's law. V is directly proportional to K and inversely proportional to M. Here V is a frequency and K is force constant or bond strength. So when the force constant or bond strength increases, that means when we are taking triple bond, here we can get the higher frequency. When we are taking the single bond, here we can get the lower frequency. So why? Because the frequency is directly proportional to K. And the next one is mass of atom. Here frequency is inversely proportional to mass. So when we are having less lighter weight atoms, so here we can get the higher frequency. So I can explain with this picture. Here these lighter atoms which are having higher frequency, and these are triple bonds which are having higher frequency. Why? Because the triple bond is having higher force constant or bond strength than double bond and single bond. So this is about Hooke's law, which is telling about bond position of the spectrum. And next, coming to the FTIR, Fourier transform IR. And this FTIR is an instrument which is very efficient. So these are the four important fundamental components, instrumental components, which are present in the FTIR. The first one is IR radiation source. The second one is interferometer, and the third one is sample, and finally photo detectors. The first one is a radiation source. Here we can see three types of radiation sources: Nernst Clover source, and nichrome coil. But in all radiation sources we can see inert solid which is heated up about 1000 to 1800 degrees centigrade. At higher temperature it is providing higher radiation. And then second one is called interferometer. Here we can have interferometer. So due to presence of interferometer here, FTIR is more efficient than dispersive IR. So why? Because this interferometer is providing all type of frequencies. So this interferometer is having three important components: moving mirror, static mirror, and the beam splitter. So when we are passing the beam, so through this beam splitter, here the beam will be splitted into two beams. So one beam is passing through moving mirror and the second beam is passing to static mirror, and this beam will be reflected back and again combined here, and it will be going through the sample. Okay, this is interferometer. Here we can achieve all type of frequencies, all frequencies that we can achieve by this interferometer. And the third one is called sample. So here the sample that we are taking is solid, sometimes liquid and gas. All type of sample can be analyzed by using FTIR. And here we are not using glass material and plastic material as sample holder. Why? Because this glass and plastic material will be absorbing IR radiation. That's why we are not using it. And this sample solution or samples can be prepared by different methods. These are the four important methods in which pressure pellet technique is most widely used one, and remaining techniques like solid run in solution technique, solid films, mull technique, etc. And finally, this radiation will be reaching to the photo detectors. And here we have three types of photo detectors: thermocouple, Gole cell, and bolometers. And these detectors will be taking the radiation and it is converting it to the electronic signal, and finally it is reaching to the recorder. Here it will be recording the graph. So here we can see the recorder and we can see the graph here. So this molecule which is having carbon, oxygen and hydrogen, and we can see the three different type of vibrations here. So there is a difference is there between dispersive IR and FTIR. So FTIR is more efficient than dispersive IR. So why? Because there is two important uh, features will be there, that FTIR can scan entire spectrum. So that means it is scanning the entire wavelength, yeah, IR wavelength. But dispersive IR is not able to scan entire wavelength, and it is taking more time also. And in FTIR, only a moving mirror will be moving, remaining all the components will be static, all the components will be fixed. And whereas in case of dispersive IR, here all the components will be moving. So that's why in dispersive IR, so we can get the less accuracy than compared to the FTIR. And the next one is called IR interpretations. Here, by using this graph, we can easily identify the different type of compounds. So we can elucidate the structure. And here we have two regions. The first one is functional group region. The second one is fingerprint region. The functional group region is there in between the frequency range of 1500 nanometers to 4000 nanometer, and fingerprint region is there in between 1500 nanometers to 500 nanometers. So this functional group region will be useful for identification of functional groups, and fingerprint region will be useful for identification of the sample components. So let me explain with the example. Here I'm taking cyclohexanol. This is the structure of cyclohexanol. So we can get two types of stretching vibrations here. So that is OH stretching vibration and CH stretching vibration at this level, that is between 4000 to 2500 wavelength range. But here we cannot see any triple bond and double bond stretching or bending vibrations here. So that's why we cannot get any peaks here at this region in between 2500 to 1500 region. But here in between the 1500 to 500 nano frequency region, here we can identify the compounds. This is the specific fingerprint region, specific fingerprint spectra for this compound. So by this way we can easily identify the sample components, as well as we can easily identify the functional groups present in the sample solution. So this is about IR spectroscopy. Thanks for watching this video, and if you have any doubts, please ask in the comment section below. And please subscribe my channel for more informative videos like this. Thank you so much. Have a good day.